I would like to, first of all, thank Dive for providing this amazing, great opportunity to be part of Qubits 2024. So I also would like to acknowledge some of my key collaborators that were involved in this project. Koji Tsuda and Ryo Tamura provided assistance in terms of the methodology, while Takanori Uzawa and his team performed wet lab evaluation part. Critical problem that anti-meiotic drugs are facing is that after deployment to the market, sooner or later they are becoming inefficient. And the main reason for that is antimicrobial resistance that infection-causing bacteria develop through interaction with antibiotics. This adaptation is facilitated directly through inappropriate use of antibiotics, as well as indirectly through pollution and global warming. As a result, antibiotics becoming less efficient and infections becoming deadly and more severe. If we look on the various mortality factors and corresponding amount of deaths they each cause currently worldwide, we can see that antimicrobial resistance is among the top runners. So if nothing is done about that, in 2050, it is expected to be 10 times higher corresponding mortality factor. So in this case scenario, all parts of the world will be affected, and humanity risk to end up in a prehistoric era when even mild infections can become deadly. So this is why new types of medicine are urgently needed. Among potential options for this are antimicrobial peptides. This is a special class of molecules that is produced by various organisms for defense purposes. Their main mechanism of action is bacterial membrane disruption, and within that, pore formation. The most exciting thing about it is that despite of coexistence for millions of years, bacteria never managed to develop any resistance against antimicrobial peptides. This is why this class of peptides is considered as a viable alternative to widely used antibiotics. However, for medical applications, antimicrobial peptides, in addition to antimicrobial activity, must possess a range of relevant functionalities, such as safety. On the other hand, most of the currently existing antimicrobial peptides in the nature, in one or another way, lack this functionality, versatility of functionality. And this is why new, for medical applications, more specialized antimicrobial peptides are needed. To address this need, we must look, first of all, on the key underlying features. Peptides are composed from amino acids. There are 20 different kinds of these in the nature, each with unique chemical composition. They are assembled in a chain, like the one shown here. Oops, wrong way. Okay. In this representation, each amino acid type is denoted by the capital letter. The number of amino acids within this chain, as well as type of amino acid at each position, may vary. These variations will critically affect peptides' three-dimensional structural features, as well as functionality. If we enumerate all possible variations, then we will see that behind that there is a huge peptide sequence space that is largely unexplored by nature or humans. This unexplored space likely contains many functionally feasible and relevant peptides that are yet undiscovered. So key objective and motivation of our project is exploration of this peptide sequence space to identify new antimicrobial peptides. For this, for guidance, we will use relationship between sequence and the property, which will form a landscape within this search space. Now, to be more specific, search space that we are aiming to explore is expected to be of the size 20 power L, where L is typical peptide sequence length, which is between 7 and 48 amino acids. Corresponding landscape is expected to be complex. Small changes in amino acid composition will likely critically affect underlying functionality. And term functionality in our setting encapsulates multiple relevant properties in addition to antimicrobial activity. We are aiming to explore multiple property landscapes simultaneously. To ensure good efficiency, we prioritize D-Waves, purely quantum solvers for navigation in this search space. Now, purely quantum or QPU solvers typically require that search space is represented in a binary format. On the other hand, our peptide sequence space that we are interested in is not in this representation. To address this discrepancy, we learn peptide binary encoding in unsupervised way using data of existing peptide sequences. For this, we exploit binary variational autoencoder, which is deep learning framework that consists from encoder and decoder network. During the training, encoder network learns to compress input peptide sequence into the binary string format, while the decoder network learns to decompress binary string back to the peptide space, ensuring that reconstructed and input sequence matching. Both networks are trained simultaneously, and what we get out of that is a binary latent space, which is binary version of original peptide sequence space. Obtained binary latent space can be used for sampling using QPU or hybrid solvers. Now, this obviously requires QUBO. QUBO in our setting must capture a relationship between molecule and property, but a priori it is unknown. So our strategy is learning QUBO from the data of existing molecules with property labels. For that, we exploit factorization machine, which is supervised learning framework. Nice thing about it is its nativeness to the Ising model. Learning relationship between molecule and the property allows to determine corresponding biases and couplings. They are learnable parameters within factorization machine setup. This enables QUBO formulation. Now, we must keep in mind that our setup is multi-objective. This implies that we must consider relationships between molecule and the various properties simultaneously. This can be efficiently accomplished by n-dimensional non-dominated sorting. To understand key idea of this method, let's have a look on this example. Let's assume we have a pool of molecules, and each molecule is represented by a point. Each point here has two labels, property I and property J. Let's assume that both properties are equally important, and that good and feasible molecules are with the high property values. The best and the most optimal molecules, according to this formulation, will be colored in pink. They form so-called Pareto front. When identified, rank 1 is assigned to them, and they are removed and not considered ever after. In the remaining population, Pareto front is identified again. So these will be molecules in yellow. Rank 2 is assigned to them. Subsequently, they are removed and not considered. Following that, Pareto front is identified again. Rank 3 is assigned to those molecules, and so on. And we continue until there are no more molecules left behind. What this procedure provides? It provides a ranking that encapsulates multiple relevant properties. In just shown example, these were 2, but procedure is exactly the same for any amount of objectives. It allows to simplify original problem, so we can focus on a single relationship between molecule and the rank. Complicated preference weight assignment to each property is not needed. We will formulate QBOR to capture relationship between molecule and the rank. Putting all of the pieces together, n-dimensional non-nominated sorting provides a rankings that captures information about multiple relevant properties. It is used to train factorization machine to learn the relationship between molecule and the rank. This enables QBOR formulation that is used for sampling from binary VAE latent space using QPU or hybrid solvers for that. Identified sequences are in a binary format. They are reconstructed back to the peptide sequence space using the decoder network. And their properties are evaluated computationally or in the wet lab setting. When the evaluation part is done, new acquired molecules with property labels are added to pre-existing molecule pool. Following that, ranks are updated, and just described cycle is repeated, typically predetermined number of iterations. We call our pipeline MOCA. We evaluated its performance on 2 tasks. First, task A consists from 3 objectives. These include charge density considered to be important for peptide interaction with a bacterial membrane. Instability index evaluates peptide structural stability, while Bowman index is linked to potential toxicity. Task B consists from 2 objectives and 1 constraint. These include antimicrobial propensity, likelihood that peptide has antimicrobial activity, hemolyticity, likelihood that peptide is toxic to the red blood cells, while solubility constraint ensures that peptides are synthesizable. This is important for the wet lab evaluation part. As the baselines, we consider a recurrent neural network, as well as random and Bayesian optimization-based sampling from the binary VAE latent space. We compare them to our pipeline with 2 different ranking setups, fixed and tunable. We evaluate model performances in terms of the Pareto hypervolume metric. For both tasks, higher values indicate better performance. And as we can see, our pipeline with both settings is performing quite well, indicating that our pipeline produced peptides are as good as or better than the baseline one once produced. From the subset of generated peptides by our pipeline for the task B, we selected subset for the wet lab evaluation. We evaluated their antimicrobial activity against selected bacteria type in terms of the minimum inhibitory concentration, or MIC. This is minimum concentration of peptides that is needed to suppress bacterial growth. And as we can see, that most of the selected peptides are antimicrobially active, so lower values here indicate better performance. Only 1 is inactive. And we see that those ones that are active are with activity comparable to the well-known antimicrobial ampicillin in this case. We can see visually, 2 pictures at the top middle, that presence of these peptides really affects bacterial population, substantially reducing and suppressing it. We also evaluated peptide hemolyticity to see whether or not they are harmful to the red blood cells. This was done by monitoring red blood cell hemoglobin release. Half of the peptides with their presence do not affect that, indicating that they are safe for the red blood cells. To summarize, these wet lab evaluation results provide important evidence that our quantum-powered pipeline can produce functional molecules that in this case are antimicrobially active and hemolyticity-free, satisfying initially set objectives. These results were published last year, so if you are interested to learn more details about our pipeline, please have a look. We call our pipeline MOCA. It is quantum annealing powered pipeline for biological sequence design. It can account for multiple objectives and constraints. It can handle various types of biological sequences, small molecules, peptides or protein fragments, and many others. Various extensions are possible. We're currently actively implementing those. I hope you will hear about them soon. But otherwise, I'd like to thank you for your attention.